Hello Year 11, this is marking of Autumn 1 Week 4 exam on reacting acids. Okay, starting with question 1. Ammonium nitrate and potassium chloride are both salts. They can be made by neutralization reactions. Now I've underlined that when I'm bugging, and to the side I've just put a little reminder of what a neutralization reaction is. Acid plus base produces what you think it is. Have a think to yourself, perhaps write it down while you're marking. The answer is acid plus base produces salt plus water. So when you read questions you should be thinking these kinds of things. Neutralization, oh yes, I know what that is. Acid plus base produces salt plus water. Choose substances from the box, complete the word equations for the formation of the salt. So these are the possible options, and these are the equations. Ammonia plus blank produces ammonium nitrate plus water. Now, helpfully up here they've told me that ammonium nitrate is a salt, so I can label that, and they've also told me that potassium chloride is a salt, so I can label that. I have labelled ammonia as a base. Now I know that ammonia is a base, that should be knowledge that you have. If you don't have it, you can write that down now. Ammonia is a base, and you will start to notice a pattern. We've got base plus blank produces salt plus water. Those savvy ones amongst you will have worked out that that's going to need to be an acid. Now, we have a look here. We've got two possible options. It could be hydrochloric acid, it could be nitric acid. So let's go back to our equation and see how the reactants relate to the products. The ammonia has gone into the ammonium nitrate there, and the other part of the salt is nitrate. Those of you who know your acids will know that the strong acids are hydrochloric, nitric and sulfuric acids. Hydrochloric acids produce chlorides, so that would be ammonia chloride. Sulfuric acids produce sulfates, so that would be ammonia sulfate, and nitric acids produce nitrate. So in this case that blank, I should be using my green pen, that blank should be nitric acid. We know that because the nitrate in the ammonium must come from nitric acid. Looking at the second equation, blank plus hydrochloric acid produces potassium chloride plus blank. Now, we know it's neutralization, so we know it's got to follow this pattern. Acid plus, so that must be a base, will produce salt plus water. So that's our first answer done. We know that's going to be water because it's been told that we've been told that this is a neutralization reaction. Now we need to ask ourselves what the base is going to be. Again, same process. Look at the products and reactants. Hydrochloric acid has gone towards the chloride part of the site, so salt. Okay, so when you use hydrochloric acid you end up with a chloride, hydrochloric acid, chloride. We know that the next part of the salt has to come from the base. So in this case we're looking for a base that has potassium. The two options we've got, potassium nitrate or potassium hydroxide. Okay, in this case potassium hydroxide is the base. Potassium nitrate is not a base, it's a salt. How do we know that? We know that bases, well, I'll tell you. Bases, those are the common acids, and the common bases are oxides, so potassium oxide, hydroxides, potassium hydroxide, or carbonates. Potassium carbonate would be a base as well. So you should know your acids, hydrochloric, nitric, sulfuric. You should know the salts, nitrates, chlorides, sulfates, and you should know your bases, anything oxide, hydroxide or carbonate. So the answer here is going to be potassium hydroxide. Okay, that's question 1 done. Moving on to question 2, let's have a look. Explain in terms of ions and molecules what happens when any acid reacts with any alkali. Now, I have underlined ions and molecules, and I've drawn a little arrow from acid and written ion. Done the same from alkaline. When you read this question you should be thinking, okay, ions, acid, ions. What is the ion produced when an acid dissolves in water. Well, I say produce, dissociated. When an acid dissolves in water, you should know this, have a little think, H+. Good. Alkali, the ion dissociated is an OH-. That should be knowledge that you have, and it's necessary to answer this question. Now, 3 marks, and we need to explain. So, let's break it down. H+ ion from the acid is our first mark. Okay, I've talked about the ion coming from the acid. They react with, you can guess what's coming next, the OH. Silly Miss Clear, she put OH+. What should it be? OH-. So, the H+ ion from the acid reacts with the OH- ion from the alkali to produce acid plus base produces salt plus water. Well done if you got that. Okay, so we've got H+ ion from the acid react with OH- from the alkali to produce water. Now, a bonus mark, I hope some of you wrote this down, would be this equation. This is called the ionic half equation for neutralization reactions, and it's writing down what I've just explained but in an equation form. H+ ion, where did that come from? The acid, well done. OH- ion from the alkali react together and produce H2O, that familiar substance, water. So, if you've done the explanation, that's 3 marks. If you wrote just the equation, you do get all 3 marks. However, I would recommend that you've written the explanation as well. Okay? If you didn't write any of this, but you did mention that it was neutralization, you do get a mark. Moving on. Magnesium sulfate is a salt of magnesium. It can be prepared by reacting magnesium metal with an acid. Good. The equation is below. Now, I've annotated here what the information they've given me. They've said react magnesium metal with an acid. So I've used my common sense here and I said, well, that's magnesium. I know that I'm reacting magnesium with a metal, with an acid. So this is the acid. Produces magnesium sulfate. How do I know that? Well, they've said it up here. Okay, magnesium sulfate can be prepared. So there's magnesium sulfate, and I know what hydrogen is when I see H2. So we've got a metal plus an acid produces a salt plus hydrogen. Question 3a. Name the acid used to make magnesium sulfate. You will notice I've put a box around sulfate. You should remember from earlier on in the video, I labelled here which acids produce which type of salt. Hydrochloric acid produce chlorides, nitric acid produce nitrates, and sulfuric acid produce sulfate. So we know the answer to 3a must be sulfuric acid. Doesn't matter how you spelt it, by the way. You could spell it with PH, as I like to, or you could spell it with an F. Doesn't matter. Okay? 3b. Use the equation to help you describe. So 2 marks, we need a description. What you would observe when magnesium reacts with the acid. Now I've put some hints on the left-hand side. When the question says use the equation, this is what you should use. Look at the state symbols. They will give you some information. Ask yourself, what will be used up, what will disappear, and what will be produced, what will appear. Let's have a look at the equation. State symbols, first of all, we know that S is for solid. So we start off with solid magnesium and aqueous sulfuric acid. We end up with aqueous magnesium sulfate and gaseous hydrogen. Okay, which ones are being used up, or which ones will disappear? Well, the reactants are going to get used up. Now, an aqueous sulfuric acid being used up isn't going to be very obvious because we're going to end up with aqueous magnesium sulfate anyway. But this will be obvious. The solid magnesium is going to be used up and will therefore disappear. So there's our first point. Solid magnesium, I'm going to write Mg, but you should be writing magnesium, disappears, goes into the solution. So they will be putting in solid, a piece of metal, and by the end of the reaction the piece of metal will have disappeared. We know that because of the state symbol and because it's on the reactant side, and the reactants get used up. The other thing that we know, the aqueous ones aren't as helpful, because how can you tell the difference? Nothing apparent. We know that hydrogen will be produced, and hydrogen is a gas. What happens when gas is produced? Bubbles! Very tempted to write an exclamation mark there, I'm not going to put it. But bubbles, gas produced, will be visible. You will be able to see that. That will be an observation that you can make. If you've labelled it, if you've said hydrogen gas produced, fine. Now interestingly, you don't get the mark for just saying hydrogen produced. You've got to have said either bubbles or gas produced. Okay, you can't just say hydrogen's produced. The final point requires a bit of knowledge, but it's an exothermic reaction, this one. So if you had said gets hot, temperature increases, or exothermic, then you would also get the mark. Okay. Right, 3C, moving on. The magnesium sulfate is in solution. How could you obtain solid magnesium sulfate from a solution? Well, I've written you a little definition here. This is the process we need. How to get a solid salt from a salt solution. And I've tried to remind you of the experiment we did with copper sulfate crystals, right? Where we'd made a solution like this, and we put it in a dish, and we ended up with, it was liquid when we put it in, and we ended up with solid crystals in the dish. What was that process called? I will tell you. Crystallization. Make sure I get my spelling correct. Crystallization, an S there because we're not American. That's the process where you get a solid salt from a liquid solution. Okay. If you said evaporation, you can also have the mark. Right. Essentially, the liquid evaporates, and we end up with a solid left. Okay. Main answer to crystallization. Evaporation also gets the mark. If you said heating, boiling, or cooling, you do also get the mark, though I think they're not as good answers. Okay, moving on. Question 4A. This question is about methods of treating water, blah blah blah. It's not important information, it doesn't need to be bugged. When chlorine is added to water, that's important because it's telling us about our reaction. Chlorine plus H2O, chemical reaction takes place. The equation's below. You've learnt now that this symbol means it's reversible. And we've got two H plus ions, oxygen chloride ions and chloride ions. An acidic solution is produced. That's important information. I bugged it. When chlorine reacts with water, which ion shown in the equation must make the solution acidic? Now, one thing that you know is that because the question said that an acidic solution is produced, then the ion must be on the products. It's not going to be on the reactant side. We're looking at the product, so it must be one of these. Okay, looking at the product side, one of those makes it acidic. Let me remind you of this question. We've already talked about it. Whenever you see mention of acids, alkalis and ions, you should know this information. Acids, of course, form H. Make sure you get your charge right. Plus ions, and alkalis, going to get it right this time, form OH minus ions. So we're looking for an acidic H plus ion on the product side. There it is, H plus. There's our answer, H plus ion. Okay, nice and easy that. If you put 2H plus, that's fine. If you named it hydrogen, that's okay as well. Okay, but we would not have accepted H2 because that isn't the ion. Now, mathematics, here we go. Write out your working I've put here. I've just been marking some mocks, and so many people lost marks because they didn't write out their working. So we need to write out our working. We've been given a formula, CaClO2, and we've been asked to calculate the relative formula mass. Relative formula mass is the sum of, you've guessed it, the relative atomic masses. They've given us, very helpfully, the relative atomic masses. All we need to do is add them together. So let's do it. Ca. There's only one calcium atom, so we're just going to do Ca times 1, 40 times 1. 40 is the relative atomic mass of calcium, and I'm multiplying it by 1 because there's one calcium atom, which is 40. Let's have a look at the chlorine, Cl2. So I'm going to write chlorine times 2. There are 2 chlorine atoms. Relative atomic mass of chlorine is 35.5. 35.5 times 2. Pop it in the calculator if you don't want to make mistakes. 35.5 times 2, 71, sounds about right to me. And finally O2, which means 2 oxygen molecules, sorry, 2 oxygen atoms. Relative atomic mass is 16 times 2, again, don't want any mistakes, 32. Relative formula mass is the sum of the relative atomic masses, so I need to add together these three numbers. 40 plus 71 plus 32. You'll put it into your calculators and you will end up with 143. That's the correct answer there. I'll just prove it to you. 40 plus 71 plus 32, 143. Moving on. Calculate the percentage by mass of chlorine in calcium hypochlorite. Right. Here's the equation you needed to use. Mass of chlorine divided by mass of calcium hypochlorite. It's like saying calculate the percentage of hydrogen in H2O. You'd need to work out the mass of hydrogen and then divide it by the mass of water and you get the percentage. So that's the equation. Well done those of you who knew that was the equation we needed to use. Now let's figure it out. Mass of chlorine, we know that that's Cl2 and we know that relative atomic mass of chlorine times 2 is 71. So we're going to write 71 and then underneath on the bottom of the equation we need mass of CaClO2, which we've just calculated is 143. 71 divided by 143, because it's a percentage we need to remember to multiply it all by 100, so let's do that. 71 divided by 143 times 100, you end up with that big old number. Okay, now we should round it. I'll write the number on 49.65034, so on and so forth. Percent. Never write a really long number like that. Always, if in doubt, round to 3 significant figures. I mean, first of all, you should check the question. The question doesn't tell me, so I'm going to round to 3 significant figures. 1, 2, 3 significant figures is 49.6, and the next one is 5, so I'm going to round up to 49.7% to 3 significant figures. Alright, that's the answer there, 49.7%. If you said anywhere between 49.6 to 50, you do get the mark. Now, moving on, 4B. 49.7% of each tablet is chlorine. I've taken that number from up there. Okay, we know that. We know that the percentage of chlorine in each tablet is 49.7%. And they've said calculate the mass of chlorine in a 20-gram tablet. Okay, here's how we do it. Let's imagine, instead of 49.7, it was 50%. This might make things easier. If I said to you that 50% of each tablet is chlorine, how much chlorine is there in a 20-gram tablet? You say, well, miss, it's going to be half. 50% of 20 grams is going to be 10 grams. Okay, if I said 50% of each tablet's chlorine, what you instinctively do is multiply the percentage by the mass and you will get the mass of chlorine. That's exactly what we're going to do, but we're just going to do it with a different percentage. 49.7% of each tablet is chlorine. The tablet weighs 20 grams, so 49.7% of 20 grams, we need to divide that by 100 of course, is, put that in, 49.7 times 20 grams divided by 100, 9.94. Now, that's fine by me, 3 significant figures, anywhere between 9.9 to 10 grams, they are accepting as an answer. Okay, moving on, 4C. Method of removing, this is some kind of background information, it's actually not important for the question. The method of removing chromium ions from water is represented by the equation. So what we're doing, we're getting chromium ions from water, putting something in, and you end up with chromium ions on their own. What type of substance will be added to provide the OH minus ions? Aha. So the question's asking what have we put in there. If we remind ourselves what we've been talking about, alkalis form OH minus ions, so the answer here is going to be an alkali. We know that because it's OH minus ions. Now, this question is fantastic. I think this is really, really good. Questions about compounds. The table gives information about the solubility of some compounds. Solubility, what does that mean? It means whether they are able to dissolve in water. Right then, soluble compounds, so things that can dissolve in water, are all potassium and sodium salts. Now, can you remember what I said salts were made up of? Let's think of some examples. They've got to have potassium in, so the first word will be potassium. And then what could the second word of a salt be? Do you remember? And was produced from a metal plus an acid. Let's have a look. If it was potassium reacting with hydrochloric acid, we'd end up with potassium chloride. So that's an example of a salt. Or potassium nitrate, or potassium sulfate indeed. Okay. It said here, all nitrates are soluble. So you can pick any metal you like and make it into a salt with a nitrate, and you've got a soluble salt. So pick a metal. Iron nitrate, for example, would be soluble. Pick another metal. Lithium nitrate would be soluble. Okay, and we can go on so on and so forth. Chlorides, bromides and iodides, except those of silver and lead. So, we've already said potassium chloride would be soluble. Iron chloride would as well. Again, pick your metal. Copper chloride would be soluble. Same for bromide. Potassium bromide would be soluble. Copper bromide, same for iodine. But silver bromide would not be. Lead bromide would not be. Okay? Now, once you've understood the table, we can move on. Use information from the table to answer the questions. Name a soluble compound that contains silver ions. Let's have a look. We've already come across the word silver. We came across it here. We know that it can't be silver chloride, silver bromide or silver iodide. Okay, we've been told that they are not soluble, except those of silver and lead. So it's not going to be silver chloride, not silver bromide, not silver iodide. We have been told that all nitrates are soluble. So that's an easy one. We know it's got to be silver, because it needs to contain silver ions, and we know that nitrates are soluble. So we can have silver nitrate as our answer there. Okay? Moving down, name a soluble compound that contains carbonate ions. Okay, well, let's look up here. It being nitrate's not helpful, because carbonate and nitrate don't go together. However, potassium and sodium, that's useful. If all potassium salts are soluble, then potassium carbonate is going to be soluble too. Potassium carbonate is one possible option. Having just told you that, you should be able to figure out the other one. Potassium carbonate. What's the other one? Sodium carbonate would be soluble as well. We know that because it said up here sodium salts are soluble. Right, metal oxides react with acids to make salts. What type of compound is a metal oxide? Great question. The answer is base. And I talked about it earlier. Bases are oxides, hydroxides or carbonates. So you should know metal oxide is a base. That's the ideal, is that you know that instinctively. Another way you could have figured it out is by knowing that base plus acid produces salt. Now, some of you might have written alkali. If you did, you wouldn't get the mark, and the reason for that is not all metal oxides would dissolve in water, and alkalis dissolve in water. You would get a mark if you said ionic. Slightly off track, but you are correct that metal oxides will have a metal atom plus a non-metal atom. Okay, metal oxide, that is an ionic bond. Okay, so ionic bonding is acceptable. Right then, more maths. Here we go. This is where it gets fun. An oxide of lead that does not have the formula PbO, so we know it's got lead and we know it's got oxygen, but that's not the formula, contains 6.21 grams of lead and 0.72 grams of oxygen. Calculate the formula. So it's going to be Pb something, O something. Right? It's not PbO. We need to work out what these two numbers are. That's the name of the game. here's how we're going to go about it. That famous equation, number of moles equals mass in grams divided by relative formula mass. We've been given the mass in grams, we've been given the relative formula mass, so I think you and I can do this. We've got lead, Pb, and we've got oxygen, and I'm going to treat them as two separate things, right? Lead, oh dear, light's gone off. Lead, the number of moles is what we need to calculate. The mass we've been given is 6.21 grams, and the relative formula mass we've been given is 207. Use our equation, number of moles equals mass, 6.21, divided by relative formula mass, 207. 6.21 divided by 207 produces 0.03. Let's just leave that there for now. Right, that's the number of moles of lead. Let's do it with oxygen. Number of moles, we don't know. Mass is 0.72 grams, and relative formula mass is 16. Okay, number of moles equals mass, 0.72 grams, divided by relative formula mass, 16. Put in our calculators, 0.72 divided by 16 gives you 0.045. Okay, once you've figured that out, you've got the number of moles. We've got 0.03 moles of lead and 0.045 of oxygen. However, we're not going to write 0.03 there. Okay, what we need is a ratio. So we need to turn this is a ratio, 0.03 of lead to 0.045 of oxygen, and we need to turn that into whole numbers. How do we go about it? Well, we could turn 0.03 to 1 if we divide by 0.03. Okay, 0.03 divided by 0.03 is 1. So let's divide by 0.03 on both sides, and we'll end up with this ratio. 0.45 divided by 0.03 gives us, 0.045 divided by 0.03 gives us 1.5. Okay, so that's the ratio of lead to oxygen, 1 to 1.5, but we can't write 1.5 there either. So what should we do to make them into whole numbers? Multiply both sides by 2. Okay, 1 times 2 is 2, 1.5 times 2 is 3, and we're there. We've got whole numbers of each. The empirical formula, therefore, is 2 atoms of lead, 3 atoms of oxygen. Let's write that in. 2 atoms of lead, 3 atoms of oxygen. Okay, I know that was a big challenge, and those who managed it, well done. Final question, and it's a nice challenge for you. Investigating the reactivity of 4 metals, you've been given powdered metals and dilute sulfuric acid. Outline a plan. We've been told that they react exothermically, which is very useful. Why is it useful? You're thinking, well, what do we know about exothermic reactions? They give out energy. Energy is released to the surroundings. What will happen to temperature? Temperature will increase. So you should hopefully have noticed that when you're answering your question. You should name your apparatus used and comment on the safe use of the chemicals. Fine. Always good to say when you're talking about safe use, wearing safety goggles. Always a good point. Goggles should be worn. There's one mark. Right then, reactivity. Well, what do we know? We know that we're going to need to react the metals with the sulfuric acid. We should measure out how much we've got, shouldn't we? So the first thing, instead of just saying a pile of metal W, let's measure out a certain mass of each metal. Okay, it doesn't matter what mass you've said, as long as they're the same. Measure a certain mass, or the same mass of each metal. That's to ensure it's a fair test. Okay, you could have said 25 grams or whatever, that's fine. Then we're going to need to react them with the sulfuric acid. What kind of equipment are we going to need? We're going to need a beaker, aren't we? Yep. You could have said a beaker. You could have said probably beaker, right? Oh, I haven't said measuring a certain mass is going to use scales. So you need to say use a balance or scales to measure the mass. Okay. Now we don't want to react them yet. We should put a certain volume of the acid. So measure a certain volume of sulfuric acid. What equipment do we use to measure volume? Well, I'll tell you. You'll need a measuring cylinder. Okay, measure a certain volume of sulfuric acid using the measuring cylinder. You'll need the same volume for each metal. Again, ensuring it's a fair test. Same volume of acid for each metal. And then we're going to react them together in a beaker. Okay, I've already said a beaker. No. We're going to put the acid into the beaker. Now, before we put the metal in, we should measure the temperature. The way I'm going to do this is by checking the change in temperature. So, before I add the metal, I want to measure the starting temperature. You can only calculate the change in temperature if you've measured the starting temperature of the acid. What should we use to do that? A thermometer. Okay, and then it's time to add the acid. This is the stage where you need your safety goggles on. Add the acid. You might have said stir using a stirring rod. Now, you probably want to use a timer to make sure that you're stirring for the same amount of time. It doesn't matter what time you've said, perhaps 1 minute. Stir for 1 minute, or a certain amount of time, it doesn't matter. And then we're going to need to measure the final temperature, or the temperature after 1 minute, or whatever you've said. Okay, so there needs to be a measurement at the start, then you react the metal with the acid, and then you measure the final temperature, again using the stirring rod. Okay, you needed a timer or a stopwatch, of course, in order to keep track of the time. And then the final point, so that's the method. Now we need to talk about how we've calculated, which is more reactive. Calculate the change in temperature is what I keep talking about. Calculate the change in temperature by doing the final temperature, take away initial temperature for each metal. Which one will be the most reactive? Well, most reactive metal will have higher temperature. Increase. Final points to say, whenever you have one of these method questions, always say repeat the experiment 3 times and always say find a mean temperature increase. Now those 6-mark questions are hard, but very, very important. Okay, you must have talked about safety, I've said about goggles, and named your pieces of equipment. Okay, and that's it. That's that exam done. Hope you've understood.